All right, so I'm going to be talking about the UT Assert Library. The UT Assert Library is a CFS tool. It's a library for unit testing. So this is the agenda for my presentation. First, we'll be going over an overview, and then we'll talk about the benefits of using UT Assert Library, and then we'll talk about the UT Assert Library components, and then we'll talk about how test cases are written and what they're comprised of, and then we'll talk about what the output will look like from a test case, and then I'll show you how to actually get the UT Assert Library if you want it. So the UT Assert Library, it's used for unit testing, CFS applications, and tasks through the use of assert statements. If you're not familiar with what an assert statement is, it's just a line of code that generates a message. It tells you if something is true or not. So each test case is self-verifying in the UT Assert Library rather than needing to be manually verified after running. So somebody was talking before about some previous thing we were using. You'd have to look at the output file to see if the results were the way you wanted them to be, but with this UT Assert Library, you don't need to do that. It tells you whether everything passed or failed, so that's a major benefit. So it can be used to test functionality and code coverage of every function in an application one at a time. Each one should be independent from every other test. So the way it works is that all CFS and CFE API library functions, such as OSAL, PSP, and CFE functions, they're automatically substituted with UT Assert stub functions and hook functions. If you're not familiar with what that means, a stub function is just a function that replaces the function and doesn't really do anything, or does the bare minimum. And a hook function is a function that you can write that would be, it would do something more if you need it to do something, but it wouldn't be the full actual function. So each API library function in the CFS has a corresponding UT Assert stub function, and stub functions, they can either return a value that you can set a value for it to return, or it can just return the default value, which is usually just CFE success or 0, or you can write a custom hook function to make it do something specific that you want it to do. Also, some functions have built-in hook functions that are called by default, and you can override those. You can tell it to call a different custom hook function, or you can tell it to just return a value. These default ones are usually in cases where you really need some kind of default functionality. So this slide is about the benefits of using UT Assert. So it simplifies unit testing for CFE, OSAL, and PSP based applications because you have these predefined stub functions, and so you don't have to worry about how the functions actually work, and you don't have to go through any complicated setup for the inputs and make sure they do everything they do right, because you just stub it out and just make it act like it succeeded. Because when you're unit testing, the philosophy behind unit testing, at least with this library, but it's general for most unit testing, is that you just want to test one function at a time and not worry about sub functions. So this helps that. So like I was saying before, a benefit is each test case is self-verifying, you don't need to comb through the output file and manually verify that the results are correct. It lends itself to good unit test coding practices. Like I was saying, each test case only tests the designated function, and that's a good thing for unit testing. And you don't need to go and make sure the sub functions are working right, because you do that separately. And it also facilitates testing of code coverage, which you can do after running your tests by running gcov. That's an external standard tool that's not written by us. And it keeping the test short and simple and just the function that you're testing. It makes it easier to know exactly which lines you're trying to cover. So it's good for code coverage. So here's what you get in the UT Assert library. In the interest of simplicity, I'm not showing the header files, just the C files, and I'll just briefly go over them. There's the UT Assert file.c. It just defines the standard assert function, which is the basic thing it's the basic function that is the center of how this works. You use it to see if things are true or not. And this file also defines some other related functions. So then utlist.c, it defines functions to create linked lists, which you need for other parts of the library. uttest.c defines the functions that you use to add and run all the test cases that you're going to run. Oops, sorry. uttools.c defines some other miscellaneous functions that are useful, but not always necessary for unit testing. Then there are a whole bunch of files for each CFS and OSAL and PSP component. There is a corresponding stubs file and a hooks file. So the stubs file defines all the stub functions. And then the hooks files, not every corresponding file has a hooks file, only the ones that need default hook functions. So not every CFE, PSP, or OSAL function needs a default hook. So if there's an entire file in their library that doesn't need any default hooks, then it's not going to have a hooks file. So this slide is about test cases. The user writes them. It tests a single condition, branch of code, etc., using the assert statements that we were talking about. You write it to test the functionality and code coverage of each function in an application, and only one at a time. And yeah, like I've said several times already, you don't want to test the sub functions. You just test the one function that you're testing one at a time. So here's a general flow chart of how a particular individual test case will work, and how you set it up and what its components are. So you have a generic setup function to initialize it. It's good practice, and what we recommend, to just write one of these for an entire test suite for an application. So one application will have one standard initialization function that you write, and you'll set that up to be run before each test case. So then within the test case, within the test case itself, this will be one function that you write within this yellow box. So you set up any variables or sub-function values or hook functions. You set them all up in the beginning of the function. Then you call the function that you're going to test, the actual function, not any sort of stub or anything, but this is the function that you're testing. You call it. And then you verify the results using the assert statements that we talked about. So you'll call a bunch of UT assert, you'll write a bunch of UT assert statements verifying things that would be modified by the function. And then there's also the ability to write a similar thing to this generic setup function, but a teardown function. And in practice, I've never had to use that, but it's there in case you need it. So here's, this has animation on it. So this is an example. The next slide is an example of what you see here. It'll be an example of this box right here. So you'll see the setup, the execution, and the verification. So.
Just a comment on teardown, if you were driving a hardware that had hardware registers and things like that, that's where you would use a lot.
Yeah, that could be useful for that. Though it could also be in the setup to initialize it back to 0. So.
Yeah, exactly.
Yeah. But I'm sure there's some case where you would need it. Yeah, so here's, you write a function name. In this case, it's the name of the function you're testing, test, then a name descriptive of this particular thing that you're testing. So here's the setup. You declare some variables. You set up any global variables or local if you're passing it into the function. And you set up any hook functions or return codes for the stub functions. And the setup could get pretty long, but this is just an example. Here's just one line. You call the function and passing in this local variable. You could also use some global variables. So then you verify the results right here. Here's the UT-assert statement, which is, well, this is sort of the UT-assert statement. This is actually a macro. I won't really get into that, but this is basically the UT-assert statement that is the basis of the entire library. This is a particular version of that function. And in practice, this is usually the only one you really need. The only version of the UT-assert statement is UT-assert true. I've never had to use any of the other variations. So you call that, and what it's doing here is it's checking a condition. It's down here is an easier one to look at. This is checking that this global data, global variable equals an expected value. Then you always have to, right after that, give it something that it'll display as the name of the test or the name of the condition on the terminal in the output. So in the output, you'll see this, and it'll tell you whether it's true, whether it passed or failed. So, and then it's generally good practice at the end to verify the number of events that you got is what you expected. So, yeah. Here's an example of some output that you would see on the terminal after running a test suite of UT-assert, and also after running gcov down here. So you get line by line coverage in the gcov down here. You can see the percents and the number of lines for each file that you're testing. And up here, this is the results of running the tests. So it'll show you the name of a particular function, a test function that you wrote, and it'll show you each of the assert statements, whether they passed or failed. So it would be like, this is the function name, and then each of these assert statements, you'd see pass or fail for each one of those. And then down here, it creates a summary, how many tests, how many assert statements you've run, how many passed, how many failed. And it's that simple.
Can I interrupt you for a second?
Sure.
Sorry, I don't know where the thing is. So I just wanted to note, on your coverage below, I know you've mentioned the line coverage, but we use this tool for the Class A work, and we found out that GCOV, with the right settings, can actually give you the information needed to tell you about the full branch coverage as well. So you can see which branches were executed, and you can also tell if every permutation of the conditions in the branches were executed. So that's one thing that we discovered, and that's why we added many more tests.
Yeah,
So
that's
I just wanted to note that you can configure it, and with a combination of this UT Assert tool and GCOV, you can get not MCDC, but at least all the full conditions and branches.
So
and
is that something that's required for Class A certification?
It's not necessarily written to be required, but if you do it, it really holds a lot of, it really tends to instill a lot of confidence.
So it makes it Class A plus.
Well, yeah, they don't even say for Class A you have to have 100%. But I think the question nowadays is more like, if you don't, why not? So if you can, then you should. So I think that's sort of the de facto guideline.
So follow that up. So when we check our components in CFF, we want to do what you just said. So you have minimal work.
We will be. Thank you. Sorry.
Wait, so when you said it gets all the possible branches, it shows you whether you got all the branches. Does it actually like go into the detail of, like, for example, every way to get into a branch? Like if there's multiple ways to set a condition, does it check to see if you did every possible way to meet that condition?
Well, yeah, so let's say you have two variables, right? An OR statement. There's 4 ways to get
Right.
down in. It will allow you to tell if all 4 of those ways have been tried.
So what if this is an issue we've been thinking about recently with some of the tests I've been writing. What if there's like a whole bunch of ways where you could set, like, say there's like a result variable that functions that you call set to pass or not pass, and there are a whole bunch of ways for it to become fail, and like there are a bunch of different branches where you could go into them and set that to fail, or other branches, and that could set it to fail, and then down below it checks whether it passed or failed. Would it check to see if you did each one of those possible ways to get into that lower branch?
I see a lot of yes nodding heads.
I don't know. I'm not sure if I'm following, but
If you set your test correctly, you can get there, yes.
With GCOV?
But you got to keep your test focused to count on what you want it to count on.
and if anybody wants, I have a presentation that summarizes how you set up GCOV to give you that data, because it's not intuitive. You have to set a -b, and you have to compile a certain way, and then you can get, and even then the output isn't clear, but we figured out how to decipher it. So I think that's
That
important.
just came up at our last CCB meeting. We were reviewing some updates to a unit test. We were reviewing the results. We were comparing those results, the new results with what we had in our baseline, and saw this extra branch, they didn't match up.
Yeah.
And the CCB agreed, wow, this is, we need to include this in there. So that is planned for the CFE, the 6.6 release. We'll be updating those unit test make files to include those new options and instructions for the branch coverage.
Yeah, I just wanted just a comment. For a lot of you here, Class A and Class B don't necessarily relate to what you're doing, but remember, we're trying to answer the question, how risky is it to use this code I didn't write kind of question, whether it's open source or somebody else's code. And I'm still trying to solve it's almost like TRL levels that we're dealing with here. And the more we can do with static checking and the unit tests, et cetera, it's simply, whether it's Class B or Class A, we'll have to deal with that. But what it's doing is trying to reduce that risk so you can make a decision to use the code.
Can people? can people still hear me on the phone?
We can hear you.
Yes.
Okay, I had one thing I wanted to bring up regarding the UT Assert.
All
I
right.
guess it's mostly for informational purposes. I mean, we like the UT Assert on the CFE side. I think it fits really nicely into the testing environment that we're using, and it's nice to have one framework to do all these tests. But one issue that we ran into is that because all of the stubs and hooks are included with UT Assert itself, that as, say, the upstream module evolves, it may get out of sync with the stubs and hooks that are within UT Assert.
Yeah, that's true.
So one thing that we did is to actually split those out. So you have UT Assert as just it's the basic framework, and then the stubs and hooks in the application that they're actually stubbing out. So it's kind of an extension of the whole thing I talked about on the CMake presentation, where you want to have all the apps be self-contained so that you pull down this module and you can just use it. It's nice to also have the UT Assert stubs and hooks with that app, just
yes.
like everything else. So it's a food for thought, and we do have some effort being made to split those out. So I just wanted to make everyone aware of that. The framework works really nicely, but we did have this kind of more I guess
Yeah.
I'd call it a management issue.
So basically, you make it so that whenever you update the CFS or the OSAL or the PSP, you have to also update the stubs and hooks rather than just like hoping that somebody will also update the UT Assert library.
Right, because the problem is if you have the UT Assert coming from this common UT Assert source, and you have stubs for, say, ES functions or SB functions, all these applications, but separately, the ES and SB are getting contributions made from other sources. They could very easily get out of sync.
Yeah.
And we've actually experienced that. So it's nice to have the stubs, the stubs that they're stubbing out get shipped with the real version.
Yeah, it makes sense.
So UT Assert is really the framework, and the stubs and hooks can move with their associated applications. And the nice thing about it is, with that model, you can extend this to cover every application in existence. You could never distribute a UT Assert that has stubs for all the CFS applications and all the applications that anyone's ever written. But if you shift that effort of providing the stubs to the actual applications themselves, then I think the whole thing can really become very useful.
Yeah, that makes sense. I guess as the number of CFS application grows, it would get harder to make sure that they're all in UT Assert.
Right. That's really the thing, is we're envisioning having lots and lots of CFS applications from lots of different sources.
The app owner.
And it becomes harder and harder to have stubs in a separate distribution that are going to be in sync with everything all the time, because everything's on an independent release cycle.
Yep.
And you could also have missions that have different combinations of apps, like an older version of one app but a newer version of a different app. And then if you're getting stubs from one source, you would have to choose one or the other. You wouldn't be able to get the right combination.
That's true.
So did you write a change request, Joe?
Well, this is what I've been talking about in the CCB meetings, as we're trying to integrate this with the Core Flight software. With this type of thing that we're trying to work through.
Susie, wasn't that the new version of the library that we were looking at recently?
Yeah, we're calling it, the library that Charles presented, we needed a way to be able to UT assert the application. So this was temporary while we work on and complete what we're calling the next generation UT Assert Library. And so that work is part, the OSAL actually, the current release of the OSAL has and uses the bits and pieces from this library for performing its UT Assert unit test. So the generic UT Assert functions were taken out, they were modified somewhat. So again, we're making like a big overhaul too of the library in this process.
Yep. All right, do we want to go on to the next slide? All right.
Do we have one more? Did you? My question is no longer relevant.
Okay, that's good. Well, there's not much of a next slide. This is the last slide, just how to get the library. So you can get it from the NASA Babelfish Git repository, or you can get it from SourceForge. And I guess I'll leave this up for a minute in case anyone wants to copy this down. Does anyone have any more questions?
I was going to have a broader comment. Is like this is what a CFS app is supposed to have. It should have a stub function. It should have an EDS. Those are the governance things we haven't worked out. When somebody delivers a CFS app, what is it? What are all the pieces? What are all the artifacts that it should have? Because so Mike Aguilar was saying, if somebody wants to reuse something, they want some confidence that it's been tested. It's not just some open source code that doesn't work. If you're going to put it into your mission, you need all these artifacts. So we need to establish what are those artifacts. This is probably one of them, that there's a UT Assert stub function for your thing, and it's gone through unit test, and it has a unit test associated with it in the repository. It's just a short list. There's probably a lot of stuff like that.
Yep. All right. Well, thanks.